Good morning, everybody, and welcome to the HEADSTART final event. My name is Sietse Kaasvaart from TNO, and I will guide you through the program today. We have a full day, or full morning, I should say, with a range of speakers from the HEADSTART project. And this is all about testing and validation of connected and automated vehicles. So be prepared for a full morning. We have a lot to tell. Good. Without further ado, let's show you the agenda. We'll first have a welcome address by Georgios Saros, our project officer. And then Carlos Lopez, the coordinator, will give an introduction to the project. And then we'll dive deep into the methodology that HEADSTART developed and put together. So that's a detailed set of presentations. Next, we'll have a short break. Before that, we'll have time for some questions and answers. But you can already raise your questions earlier in the chat. Good. After the break, we will go in specific use cases that we tried the methodology on, and we will look at special user groups that for the methodology, the HEADSTART methodology, and see what this means for them. Next, we go to key enabling technologies. So HEADSTART introduced or focus on three key enabling technologies, being cybersecurity, positioning, and communication, or V2X. And then we'll end with an evaluation and conclusions and a closure. So that's our full program. Let's move on. This project wasn't possible without the funding and the support of the European Committee. And to make sure that we work on the right things and do these in the right ways, the project is guided by Georgios Saros, a project officer at CINEA. And CINEA in full is the European Climate Infrastructure Environment Executive Agency. So it's a full title. So CINEA, I want to give the word to Georgios Saros, and he will welcome us to the project. Georgios.
Thank you very much, Sietse, for this kind introduction. Can you see all my screen now?
You need to go to presenter mode. Yeah, we see it.
Okay, good. So, good morning, everybody from Brussels. Fortunately, due to current circumstances, again, this is another remote final event that the project actually should organize. And I hope that we all very soon meet again together in order to further discuss the developments that actually are happening in this domain. So my name is Georgios Saros. I'm a project manager in Horizon Europe Transport Unit in CINEA. And my project portfolio actually is dealing with automated road transport project, and HEADSTART is one of them. So what is CINEA? As you may know, the climate infrastructure, the European Climate Infrastructure and Environment Executive Agency, in short CINEA, was established by the European Commission for the implementation of the financial programs that underpin one of the main priorities and objectives of von der Leyen Commission, which is the European Green Deal. In addition to the legacy programs such as Horizon 2020, where HEADSTART project actually is funded, CINEA will be managing several new programs and the total budget for all these programs will be around to 55 billion euro for the period for the next framework program, which is from 2021 until 2027, which of course will contribute to decarbonization and sustainable growth. CINEA implements Horizon Europe collaborative research and innovation actions under Cluster 5, which is on climate, energy, and mobility, where research and innovation in transport plays, of course, a key role in achieving the ambition targets that the EU has set in these key areas. You remember that specific goals have been set for 2000 until 2030 and until 2050, which is of course the ultimate goal to have a neutral continent in Europe. Under Horizon Now Europe program, a dedicated sector for the implementation of automated transport projects has been established in CINEA. And I am part of this team. So the team actually will be responsible for the projects on automated road transport. And the establishment actually of the sector, it shows the importance that the new agency gives to this area. CINEA staff is committed to ensuring high standards in delivering operational tasks linked to proposals evaluation, preparing the grant agreement for the successful, of course, proposals, and in managing the projects along their life cycle until the project closure. So it's a proper continuation from what INEA did in the past, and now CINEA actually took over all the responsibilities that INEA had in the past. Of course, you already know that the new research and innovation framework program, Horizon Europe, was launched a year ago. But I would like actually to present you a few statistics of automated road transport projects funded under Horizon 2020. So you see that the Horizon 2020 automated road transport and mobility for growth calls, plus the ICT calls, were the main contributors towards the achievement of main targets. In that frame, you will see on the first pie that during the period 2014 until 2020, 18 sector-specific topics were opened for proposals. Of course, the majority of them comes from ART topics, but at the beginning of Horizon 2020 framework program, we had also topics on mobility for growth related to automated road transport. We had also interesting calls and topics in ICT, close related to 5G communication. And in total, there are more than 30 projects that they were selected. The majority of them, as you can see from the pie, more than half of them actually are research and innovation actions. But also we have some innovation actions projects dealing with large-scale demos and pilots that take place not only in control environments, but also in real traffic conditions. In the third pie, actually, you can see the actual status of the projects until the end of 2021, so until the end of this month. Unfortunately, due to COVID situation, a large number of projects actually have requested for an extension, which of course also explains that the majority of the projects are still ongoing. And in the graph below, you will see the distribution of EU funding along the framework program of Horizon 2020. So you will see that in 2018 and 2020, we have two peaks there. And this actually explains because we have the introduction of the ICT calls, of the 5G calls. And this explains actually why the funding was higher during these 2 years. In total, the total funding of in this domain in Horizon 2020 was about 350 million. I would like now to just to give you an overview of the recent developments and more precisely to highlight some of the flagship projects in Horizon 2020, where actually most of them are still up and running, and they actually pre-produced now very useful results, which of course can be can be used as a tool for the next framework program, Horizon Europe. So you will see here three, let's say, main categories of these flagship projects. So L3 pilot project, organized demonstration at large scale in various EU member states and cities. And the newly EU-funded project HyDrive, which can be considered the successor of L3 pilot, will push automated driving further towards high automation. The feasibility of high-level automated driving in very different conditions and driving cultures across Europe will be tested. The next big group is the fully automated urban road transport and shared automated vehicle fleets in urban areas. Here we have two projects, Avenue and SO, which focus more on shared mobility in urban environments. They implement full-scale demonstration of urban transport automation by deploying fleets of automated vehicles. In Avenue, the type of vehicles that is used is mainly automated shuttles, but in SO, except shuttles, there are also other type of vehicles like bus, cars, and delivery robots. They implement a full-scale demonstration, as I said, of urban transport automation by deploying fleets of automated vehicles. And they target, among others, people with disabilities, elderly people, and vulnerable users. We should not forget that, for instance, in Avenue, the target is to introduce this type of vehicles in public transport service. So it means that the criteria and the prerequisites to run a public transport service are very strict, and you need to consider all different groups of people that who can actually move with this vehicle. And they try to maximize the personalization and optimization of itineraries and aim to make traveling actually a real experience for each passenger. The current tests are providing valuable data to evaluate road behavior, security of all the automated vehicles, and passenger safety. To finish with the examples, the third group, we have the projects Ensemble and
So in our way of working today, it's rather straightforward. You can already raise questions by writing the GoToWebinar chat. Some of the questions we will be answered during the presentations in writing. And questions that we do not have time for, we will make sure that we answer them afterwards, again in writing. So a selection of questions will be raised to the speakers at the end of each block. So just before 10:30, we will do that. And it takes a bit of timekeeping. The better we do the timekeeping, the more questions we can bring to the audience. The session is being recorded, so that is something that you should be aware of. And the presentations, yes, will be presented on the HEADSTART website next week or in this week. You will receive a message when they are there. Good. Before we start on the content presentation, we will have a couple of small polls today just to collect your opinion. So let's try one. And this is on the commuting distance to where you are at this moment. So some of you will be at home in the comfortable environment with their own good coffee. Others will have gone to work, and so we'd be interested to see where you are today. What's your commute today? Okay. Good. I'm going to close in a couple of seconds. It means we have a score of 71% of attendees working from home, which is quite a bit. And then there is 10% up to 10 kilometers and 90% up to 100 kilometers. So commuting is still there, but with the 71%, I guess we do a tiny contribution to the Green Deal and avoiding traveling time. So good to hear you're back and attending from home mostly. Let's go to the next speaker, and that is Carlos Lopez from IDIADA. He's the coordinator of the HEADSTART project, and he will present to you the introduction of the project. What is the project about? What is the scope? So Carlos, can I give the word to you?
Yes, thank you.
I will.
Thank you. Very much. Okay, so I will share my screen. Okay, just 1 second. Yes. Okay, so I want to introduce a little bit what is HEADSTART, the main facts of the project. HEADSTART is as we already mentioned, is an Horizon 2020 European Union funded project in the call of RT01 2018. It is a research and innovation action. This means that it's focused on advancing the technology readiness, but it's not, let's say, focused on its commercial deployment. Okay. The project had a total duration of 36 months, so 3 years. We are starting in January 2019. and we are just about to finish now in December. So that's why we do today this final event, to show you the results of all these months of working. The budget of the project was 6 million euros. We have been 17 partners in the consortium. And okay, my name is Carlos Lopez. I am project manager at IDIADA, and I am supporting Xavier Sellart also in the coordination of the project. We have a website. Here you can find the address. We invite you to visit us and to download all the information that you can find there. And we are also present in the social media, in Twitter, LinkedIn, Facebook, etc., etc. Which is the consortium? So the consortium is, as I told you, is formed by 17 partners. Partners distributed for all around Europe, because we wanted to include the expertise of different organizations. In the consortium, we had 7 research centers, 2 technical services for type approval, 3 accredited Euro NCAP laboratories for consumer testing, and we also had the presence of the industry in our consortium, because we had 4 OEMs and 2 tier 1s. The consortium was built in a way in which we wanted to bring together the expertise of coming from testing, validation, and certification on connected and automatic driving around Europe. Not only regarding European project levels, but also the expertise of the different countries and organizations from each country. For example, we have in the consortium 3 coordinators of H2020 IRT calls. Okay, but also some of them, some of the participants in the consortium, they are also leading important are important partners of activities that are done in their respective countries. Just to have a short overview of how HEADSTART was structured, the project, we had 7 different work packages. In work package 1, that was led by BDCOM, we did the selection of the use cases, and we defined the requirements. In work package 2, that was led by IKA, we created, let's say, the methodology and the procedures of the methodology. In the 3rd work package, led by Virtual Vehicle, here we defined the architecture, the environments and tools for later on applying these tools in our use cases. That was done in work package 4 and was led by TNO. And in our different demonstrators that we have to demonstrate the methodology. In parallel, or a transversal activity was managing work package 5 that was led by Ertico. Here we had the communications with the different expert community related to connecting and automated vehicles. And finally, in work package 6, led by ICCS, we did the communication and the dissemination of all the activities we have done during the project. The coordination was done by IDIADA in what we call the work package 7. Which is the concept of the project in a very, let's say, generic way. So we can say that the project is split in 5 main activities. The one is the first step, let's say, is to the selection of the scenarios from existing databases. Then at this time, we introduced what we call the key-enabled technologies there, the parameters of the key-enabled technologies that in this project are the cybersecurity, the positioning, and the communication. The next step was the allocation of these scenarios to the different test instances. Next step was the execution of the test, virtual testing, provincial testing, and field testing. With the results of this testing was evaluated, And finally, these results were harmonized and shared with the rest of the community. Which are the objectives of the project in an overview? So HEADSTART defined testing and validation procedures for CAD functions, including what is more innovative, let's say, the key-enabled technologies that, as we said, are the communication, cybersecurity, and positioning. By cross-linking all the test instances, such as simulation, proving ground, and real-world testing, this is something that is more common now, but in the moment in which the project started was quite innovative, with the objective of validating the safety and security performance according to the needs of the key user groups. In our case, in our project, the key user groups were the technology developers. Okay? What we can say is the industry, the OEMs, the people that is going to implement this technology later on. Also, the consumer testing. Consumer testing, for those that are not familiar with this, could be, for example, Euro NCAP, and also type approval instances, so homologation instances. And we did it in 5 different stages. Okay, the first stage was the identification. In the identification, what we did is to look and analyze what was done at that moment in the world related to CAD. In the second stage, we tried to harmonize all this information, finding commonalities, differences, gaps, with the aim of defining a unique methodology that unifies all these, let's say, other initiatives that we found in the first step. On the third stage, we did the definition and development, where we took all these commonalities and we started to create all the tools, all the procedures to assess the connecting and automated driving functions that we demonstrated on the fourth stage, applying these procedures to our use cases, and finally, another important stage was to reach consensus. So to let's say do a transversal work in which we created an expert network, and we had different dialogues with the community, with the experts, with the different stakeholders, in order to have 3 main objectives. One was to show our progress in different workshops, get the feedback from the experts and trying to apply their experience by improving our methodology, and then steering a little bit the work on how we should go in the future. Okay, so these are the 5 main objectives of the project. Here, what we want to do is to show you a short video that could be very interesting, because it's 1.5 minutes, but it gives a very good overview of the project. So please, Julie, if you Okay, thank you very much. So how you can be connected with HEADSTART and where you can get the information from the project. So our main source of giving you information is our website. Here you can download our deliverables. You can see the results of our workshops, etc., etc. As I told you before, you can also follow us in the social media. You can reach us via email, or you can sign also to our newsletter. You can also get in touch to our partners if you need any support or any information regarding our deliverables. For instance, what I want to show you now is the list of deliverables that will be, or that are already available in our website. Some of them, as I told you, are already available. Some others will be released and published very soon. They are split by the different work packages of the projects, as you can see. Okay. And finally, just to mention and to have an overview of which are the 17 partners of the project. As I told you, any doubt, anything that you want to ask, please follow your questions to our partners that we will try to answer you as soon as possible. So this is all I wanted to say about the HEADSTART project in a general, let's say, point of view. Thank you.
Thank you, Carlos. Thank you. So I think it shows very well the width of HEADSTART. And let's now move to really the methodology that was developed, because then we go into the details of what the project realized. So our first speaker will be Nicholas Wagner from IKA in Germany, and he will present on the overall methodology and show you how that's set up. So Nicholas, I give the word to you.
Thank you, Sitze. So yeah, my name is Nicholas Wagner. I will present to you the HEADSTART methodology together with Bernard and Xavier later in this presentation. So for the overview for this presentation, first I would like to give you short motivation for the need of a combined methodology for the safety assurance of connected and automated driving functions. And then I would like to show you the HEADSTART's overall methodology in a nutshell. Of course, we cannot go into every detail, but to give you an overview. Then we would like to show you a short safety argumentation for the various stakeholders based on the overall methodology. And finally, then we go into separate talks about the insights to key topics within the methodology, which we think are important and need further instructions. So where does the HEADSTART methodology come from? So there are a lot of different initiatives and projects in the EU, in national and international projects, also worldwide in Japan or in the United States. There is a lot of state of the art, and this was the first part, which was already introduced by Carlos, that we did a state of the art analysis. And it shows that there are a lot of differences, but there are also a lot of communalities. Therefore, we wanted to harmonize the present and past projects into a combined methodology, utilizing common databases to analyze the data and to test then relevant selected scenarios. There arises the question, why do we need scenario-based safety assurance? So it's quite simple, and I think it's in nearly every talk about scenario databases or scenario-based safety assurance. But just let me go quickly through it. So you could assure the safety by test drives, but there are sample calculations ranging up to billions of kilometers. And that would be necessary for each update of the driving function. So this will just not be feasible to drive around with every new update, or even with one update, billions of kilometers in the open world. And then there could be safety assurance by expert knowledge, but currently there is no evaluation methodology available for automated driving level 3+. So we have a lot of concepts for functional safety, but not for automated driving. So it is just not available. So therefore, we need a new methodology, and I think the basic concept is also quite well known, but let me also go quickly through it. So we have a few different steps in this overall methodology, and this is just an introduction to that. So we begin with input data. So we collect all the data in the open world, which is necessary to test such a connected and automated vehicle. And then we integrate it by database mechanics into a so-called scenario database. And this integration is a crucial part. So there need to be scenarios extracted, and it need to be defined which scenarios are there, and then they are integrated into such a scenario database. From the scenario database, we select output. So we select scenarios from this database based on the driving function and allocate the scenario to different test instances. So we can allocate to simulation, of course, which is highly efficient, but also to X in the loop or proving grounds, which gives us more confidentiality into the test. And then finally, there's an evaluation. So what we do is that we do not drive around billions of kilometers, but with one driving function and use it as a test, but rather drive around a lot of kilometers with different vehicles and different sources, and thereby store like the real world and scenario database, and then use this scenario database to test any driving function later on. So the HEADSTART methodology looks quite similar, but more detailed. So you will find the different aspects from the last slide on this slide as well. So beginning with the input data, this could be field data, aerial data from drones, accident data, simulator studies, infrastructure data. So these are just a few on this slide, but there are more inputs possible. This just shows that there are different inputs. And then there comes the large part of the scenario databases. So we defined it within HEADSTART, but we used existing databases. I will come to that point later on. So we have the input data, then there will be a pre-processing, and then the crucial part, the scenario extraction, based on possibly a 6-layer model within HEADSTART. Also, this will be on a later slide. Then there will be a post-processing and extraction of parameters, and the scenarios from this continuous drives in the open world will be saved in a scenario database with parameters to be rolled out into the test. And all of the database mechanics, which is within the green part, is not based on a specific driving function, but it rather just shows what is happening in the real world. And yeah, we do not have so many kilometers yet, or we might not have so many kilometers yet in any project. So there can be injected scenarios for completeness and expert scenarios which are necessary to test for regulations, for example. So this is the right-hand side. Then when we roll out the scenarios, we are looking into the driving function and the use case. So especially the operational design domain is quite important. And based on this, we select relevant scenarios from the scenario database with a query to any scenario database, and the output will be like the exposure, the logical scenario itself, and the parameter distribution according to that logical scenario. Or if you roll out multiple logical scenarios, of course, there will be multiple logical scenarios with their respective parameter distributions. So within the parameter distribution, we can then do a parameter variation to derive concrete scenarios. So to test more of the parameter space, we can do this parameter variation. And then we get the concrete scenarios. And yeah, now comes a quite specific part to HEADSTART, which will be in the second part of this whole final event. So we add the key enabling technologies, the communication, positioning, and cybersecurity parts to the concrete scenario. We do that at this late stage because we do not build up a scenario database within the project, because there are so large projects which look into the scenario database, have a lot of work going on in scenario databases. To name a few, there's like TNO Streetwise, Pegasus, BNB Methods, Move or MOSA, and many more. And in HEADSTART, we just want to define the general work process with the scenario database, and then just access them and use them. So therefore, these scenario databases are not specifically focused on the HEADSTART key enabling technologies. So therefore, we add the key enabling technologies on this later stage. So with the concrete scenarios, we then go to an allocation of scenarios. So we look into the different capabilities and requirements of the test and the capabilities of the different test instances, like the virtual simulation, X in the loop, and proving ground. And of course, we try to allocate most of the tests to the virtual simulation because it's quite efficient. But there might be some requirements to go to X in the loop based testing or even to proving ground testing. And then the scenario is rolled out into the test. And yeah, then finally, we can evaluate the test with pass-fail criteria based on the use case and the driving function and the human capabilities. So we need to compare it to the human in the evaluation. And then finally, the results can be brought back into the database, of course, but also in the selection of relevant scenarios and stochastic variations to look into specific parts of the parameter space in a more detailed way. And then finally, we found out that the cybersecurity assessment is kind of a different topic. Of course, some small parts can be in this concrete scenario, but there need to be a different, separate cybersecurity assessment, and then this is done in the evaluation because it's quite different from the scenario-based testing itself. So for the safety argumentation, we have identified 3 coverages. So we have the coverage of scenarios, the coverage of concept, and the coverage of tests. So the coverage of scenarios is there enough input data? Is the database content complete? Which tells us, do we have enough of the real world recorded? Do we know enough about the real world to have all the scenarios in there which are relevant to test the driving function? Then we have the coverage of concept, which tells us, is the concept able to include all the relevant aspects? So are there enough parameters to describe everything what was happening outside to bring it back to the simulation or to bring it back to the test in general? So this is the coverage of concept. And then we have the coverage of test, which is the selection of the parts of the scenario database. Is it enough? So is everything covered within the scenario database? And if we comply all the 3 coverages, we have a good safety argumentation. So we have all the scenarios from the real world. We have everything recorded, what is there in an ideal world. Then we have everything within our concept, and finally we have everything tested from this database. So then we can say we can have a valid argument in the end. And yeah, to make it more detailed, we have, like, in a perfect world, we have the statistical complete real world recording. Then we have an abstraction of real world of all the relevant aspects, and we derive a complete database, so everything what is happening outside. Then we have an ex post evaluation of pass-fail criteria in all the different scenarios, and finally we have the safety argument. So this is not really the real world, because we only have a current status of real world recording, because we cannot have like everything recorded because that's not possible. So then we can only abstract the relevant aspects and have a semi-complete database. And that's why we need an analysis and creation of expert scenarios to make the database more complete, even with the current status of the real-world recording. Then we have a mapping of parameter space on the relevant scenarios, which is just the relevant scenarios, and we include the key enabling technologies to make it to cover more aspects. Then we have the analysis of the exposure, which gives us an idea of the exposure of the relevant scenarios, because we cannot test in all scenarios, and therefore we can still have a safety argument, but we know now how the statistical background of the safety argument, because we know it of all the different parts within the safety argumentation. So now I would like to just shortly go into the first part. So the second part and the third part will be in separate presentations after this one, but I would like to shortly go into this first part. And as I said before, we used existing databases from large national and international projects within our demonstration, and we identified that it is just not feasible for us to create our own database within HEADSTART, but we rather wanted to define the interfaces to the databases, how to work with the databases, and what needs to be in there within our overall methodology. So therefore we identified the six-layer models, six-layer model originally coming from the Pegasus project, but used widely in the international context. So there are 6 layers, and everything I would like to say is that there are a lot of different scenario concepts within the scenario databases. So there are different concepts like cut in, cut out. Then there are concepts like the challenger concept or whatever, and all the different concepts are necessary, but for us it is just important that the concepts include all the 6 layers, and these 6 layers are kind of arbitrary from the underlying scenario concept, because we want to identify all the relevant aspects which happen outside, and therefore the 6-layer model is quite well suited. So on layer 1 there's the road network and the traffic instructions, so like the road geometry, the traffic signs. Then we have on layer 2 the roadside structures like rail guards, trees and buildings. Then on layer 3 we have temporary modifications of layer 1 and layer 2, like road construction, traffic cones, everything which is just a temporary modification. Then on layer 4 the dynamic objects, which include vehicles, pedestrians, cyclists, but also animals, for example. So everything that is dynamic and moving. So layer 1 to layer 3 is kind of static, and layer 4 is then a dynamic layer. Layer 5 is the environmental conditions, the light situation, the weather, if it's raining or snowing, or if it's whatever happens outside. And finally layer 6 is digital information like V2X information, but also a digital map, for example, stuff like this. And what is important to us is that on each layer all the relevant aspects are then extracted and saved into parameters and are regarded within the scenario concept which is underlying behind the database, and we get information on all the 6 layers and can use them to then roll out the scenario into the test. Okay, so that's it from my side. And I would like to give over to the selection of the relevant scenarios and the allocation of the scenarios to Bernard.
Thanks, Nicolas. And indeed, we move to Bernard Hilbrands, who is from the Virtual Vehicle Institute in Graz in Austria. Bernard.
So thank you, Sietse and Nicolas. So my name is Bernard Hilbrands from Virtual Vehicle. And I want to give you more insight into the scenario selection and allocation part of the methodology. So this part is represented in the methodology by 5 main boxes. So the input, the scenario database, the scenario selection, the scenario allocation, and the CAT enrichment. And I will go through them one by one, and of course starting at the beginning. So when we want to start the procedure, it's necessary to have all required input information, and because otherwise meaningful safety validation of the automated driving function is not possible. So this input includes, for example, the dynamic driving task, DDT, and the operational design domain, the ODT, that defines under which circumstances the automated vehicle can execute the DDT, and at the same time it defines the limit of operation for the function. So the ODT is very important for the execution of the procedure, but there are not many standards or tools available at the moment to support this part of the methodology. And I quickly want to mention the PAS 1883, which is a specification defined by the British Standard Institution, BSI, and it was first published in August 2020, and it's divided into 3 sections. First, the scenery that covers the road and everything that has to do with it, the road infrastructure. Then we have the section environmental conditions, with illumination, with the weather, but also connectivity, like communication and positioning. And then we have the part of the dynamic elements, which covers the vehicles and other road users. And with this specification, an ODD can be defined quite well. And also I want to mention the ASM Open ODD, which is currently under development, but was not available for the HEADSTART project. If all the input information is available, then we have to look at the scenario databases. So in HEADSTART, we have cooperated with several different databases, and that have the common goal to enable testing and validation for automated driving functions under controlled situations. But despite that, they have their own definitions, they have their own data formats, and so we had to define an approach for the harmonization that contains several points like defining an ontology, a query language, and the data content. And for that, labels can be produced from real data, which determine the exact spatio-temporal values of an object in the scene and their geometric properties. So actions and their temporal occurrence can be described in such a way. And the higher level part of the labeling can be expressed in a list of resource description framework triples, RDF triples, which then constitutes the ABOX statement list like the one that you can see on the slide here. When the scenario is expressed in such an RDF format, it is possible to treat it as a graph and therefore use a graphical database such as a Neo4j. And the direct use of this graphical expression of scenarios is to create such queries. And querying the scenario databases can be interfaced by a harmonization layer that offers query services containing concepts and relations from the ontology. And the scenario database can then be accessed with a semantic query language such as Sparkle or Cypher. The databases then selects the relevant data and converts it into the requested output format. Currently, open scenarios is the most promising data format, and the selected scenarios then made available in a data bundle, like that includes the open scenario file, an open drive file, and ideally also a file with a parameter distribution. As Nicholas said, the database itself was not part of the HEADSTART project, but we were in close contact with the responsible persons of, for example, Streetwise, Move, and the Pegasus database. Next, it has to be checked if the chosen scenarios that we receive from the database are inside of the ODD, and if the scenarios from the database already cover a significantly large part of the ODD and tests all the relevant functionalities. And this has to be checked to ensure a sufficient safety evaluation of the driving function. If this is not the case, then more scenarios need to be added. This can be done by another scenario database if this is available. If this is not available, then it has to be done by experts. And also, as Nicholas mentioned, to have enough coverage to form a safety case for the driving function, it's important to evaluate one scenario description with as many different parameter combinations as possible. But of course, this also means that the efforts of the tests increase, and therefore it's very important and it's necessary to evaluate the importance of the individual parameters. And to be able to vary and combine the relevant parameters in a meaningful way, the corresponding parameter distribution is required, because otherwise it's not possible to make a distinction between scenarios which are unlikely and typical traffic scenarios that occur relatively often. So ideally, this information will be provided by the database. If this is not the case, then the distribution must be defined manually by experts. Then the next phase is the scenario allocation. So here the scenarios will be allocated to the testing methods, but before this can be done, the capabilities of the testing methods for virtual testing, for accident loop-based testing, and for proving ground testing have to be specified regarding their sensors or sensor models, their environment or environmental models, and the vehicle or vehicle dynamic models. And with this information will then be combined, and we called it a map of capabilities. And the allocation faces then different branches. And the first one allocates the scenarios from the database to 1, 2, or all 3 of the testing methods. And to do this, so for this purpose, the requirements of the scenarios are compared with the capabilities of the testing methods. And in this way, it can be determined which of the testing methods are suitable for each of the scenarios. And of course, the final decision, if all possible testing methods will be used or just some of them, can then be made by the target group. And then there's a second branch for the scenario allocation, and that is very CAD specific. And with CAD, I mean in this case, communication and positioning, especially. This branch is optional and will only be executed if scenarios should be enriched by communication or positioning related parameters. So in this case, a logical layer for communication or positioning with additional parameter distributions will be produced. And with this information, allocation to either real-world testing methods or virtual testing methods will then be made. And at the end of the phase, we have created test cases that are allocated to at least one of the available testing methods. and this then ends the part of the scenario selection and allocation of the HEADSTART methodology, and it continues with the testing part, which will be the content of the next presentation. Thank you.
Thank you, Bernard. We have a seamless handover to the next speaker, which is Xavier Sellart from IDIADA in Spain. So, Xavier, the floor is yours.
Thank you, Sitz and Bernard. Okay, so my name is Xavier Sellart, and I will explain the last part of the methodology. Okay, so basically, the last part of the methodology is to execute the allocated scenarios that were defined in the previously part of the procedure. Okay, so one of the important parts of this part of the procedure is to have a coordination, because at this stage we have a set of scenarios that are going to be executed in the different test platforms, but also we need to define a strategy on how those scenarios will be executed in each. Okay, so basically, another important part to say is that each project can have their own test methods or their own specific test tools, but we have divided the test methods in four main ones: no? Virtual testing, chill testing, proving ground testing, and field testing. Okay, so here I would like to show one specific example related to test coordination. Okay, so for example, in one of the linked projects, which was Ensemble, track platooning, there were used three main test environments, which were virtual testing, chill-based testing, and proving ground. And one of the challenges in that case was to ensure the communication part before going to the test tracks. Okay, so then that's why the two test methods were more interesting to be executed in the first part of the scenario-based validation, and lastly, the proving ground was executed in the test tracks. Another example of coordination is one of the scenarios that we have studied, for example, for Agile chaos regulation. In that case, we were one of the needs of this kind of scenarios were that we're having many variations and combinations, and that's why we were using the virtual part in order to validate a huge number of test cases. And then we were using a chill environment to validate some corner cases in the test tracks, and then using the proving grounds in order to assess the complete system in the proving grounds. And lastly, another interesting was to use field testing in order to gather or to look for scenarios where we were capable of demonstrating that the system was working also in real world conditions. Okay, so next is I would like to go more in the details on each of the test methods. Okay, so first of all, I would like to mention the virtual testing part. Okay, so basically the main usage of or objective of the virtual testing is to be capable of executing a large number of test cases. Okay, this is basically the test method which is much efficient, but also is the one which is less realistic, because you need to have a very accurate models in order to make it as good as the other test methods. And in our test method description, we have four main blocks. One is the part of the driving function, which basically is consisting on having the control logics of the driving function. Then there is the part of the vehicle dynamics, which is everything related to the dynamics of the vehicle. And then the sensors, which is one of the challenges in the part of automated driving, to have good correlated models. And then we have the virtual environment, which is related to the capability of simulating scenarios in the simulation tool. Then I would like to continue by explaining the procedure. Okay, so basically the procedure for virtual testing is divided in three main parts. First of all is the preparation. Okay, so in virtual testing, one of the relevant parts is to have good plan models in order to have a realistic simulation. and also is to generate the scenarios that need to be executed in the test tool. Later is to execute the scenarios in the virtual environment. But there are different, let's say, tools available, but as soon as those tests are executed, then we have the data that later on is used to evaluate the different KPIs that has been defined for the specific test case and scenario. Next part, I would like to continue by showing some of the test linked projects that where this HEADSTART methodology has been applied. For example, the first one is about the Valeo, that they have a tool that was used to validate the positioning system, as it can be seen here. Okay, so basically, also this tool and this platform could be used also for validating ALKS scenarios. Okay, they are using IPG as a simulation environment, and basically they can automate a huge number of scenarios. Here is another example from virtual vehicle, and also it's validating ALKS scenarios. And here also we can show the different ways of assessing the virtual part by using different simulation tools. And here we would like to show also another setup, which is a hardware in the loop setup, where we were also evaluating a connectivity feature in a highway, where we were showing how the scenario was assessed by a hill setup where the communications were real, because before going to test in the test tracks. Okay, here we can see that in that case we were using PreScan as a simulation environment and a prototyping tool from IDIADA for the driving function part. Okay. Okay, so this is all about the virtual testing method, and next is to talk about the chill testing. Okay, so basically the chill testing method is more about having a physical part of the system and a virtual part of the system, and this is a quite interesting test method, because sometimes in some of the projects we are not having the accurate plant models, and the chill testing was allowing us to validate a large number of scenarios without the need of having the complete driving function and reducing the complexity in the physical testing. Basically, this test method we divided in two main setups. One was more about the driver in the loop, and the other more about the vehicle in the loop that we will show at the end some examples. Okay, so chill testing, in that case, the preparation is much complex than virtual, because in that case we already have a physical part. Okay, for that reason, here is really important to have a commissioning of the setup before we execute the test cases. And then as soon as we have the setup prepared, we go to the execution part, which basically needs to have a good synchronization between the virtual validation tool and the test tracks or the tools where the system or the scenario is deployed. And then you have the evaluation, which basically consists in extract the metrics that were defined for the specific scenario. Here in the following video, we can see some of the linked projects where we were using chill test method. Okay, in that case, we can see the driver in the loop setup that was deployed by a virtual vehicle for the automated drive demonstrator. And here we can see how the same scenario that was previously shown for AL carrier regulation is demonstrated by driver in the loop setup. Here we can see also another setup from IDIADA, where in that case we use a driver in the loop setup, but in that case we are using a driving simulator that is already having the dynamic part of the vehicle. In that case, it's a driver in the loop setup, but we are also adding the dynamics of the car. And here we have the other setup, which is about vehicle in the loop, where we can show a safety scenario, a corner case in the test tracks, and in doing it in this way, it's more efficient than starting from scratch in the physical testing method. Okay, so next test method that was also assessed and demonstrated in our methodology was the proving ground testing. Okay, so basically the main advantage of the proving ground testing is that we are evaluating the complete driving system, but in the other part it is more expensive and more complex to be executed. Okay, because we need real targets, we need real vehicles, we need everything, and that means that is quite complex to be executed. Okay, so that's why it's one of the methods that normally we do at the less number of test cases compared to the others. Okay, so for this test method, there are two main things that need to be considered. Okay, so first of all, is to, during the scenario allocation, is to provide feedback in order to define which of the test cases can be executed in the test tracks. At the end of the day, not everything can be executed in the test track. There are some limitations depending on the proving ground, and I think it's quite relevant not to provide this feedback to the scenario allocation procedure before we allocate the scenarios in the proving grounds. And then is to do the execution of those scenarios in the test tracks. Here, normally the preparation is similar to the chill test method, but in that case we are also including the need of simulating the real targets. Okay, so this means having synchronized driving robots, having base stations for having a high accuracy GNSS positioning system for the robots and the systems, and also means to have the next step, which is about the execution of those test cases in the proving grounds, where later on this data is stored. And then the last step is, as usual, just to compare the KPIs that are defined in the test matrix for the proving grounds in order to evaluate the acceptance criteria that has been defined for each. Here we can see some examples. Okay, so for example, we see the complexity of for example, evaluating a driving function which is about connectivity. In that case, the system is not yet anymore one car, it's a fleet of trucks. No, that's why the logistics for proving grounds or test tracks are quite relevant. Okay, in that case, it's really important to have a good coordination of the test cases and to define the right order in order to ensure that the system is working as expected. No? Here we have another example from Veoneer evaluating some deceleration scenario with a real target. And here also we can see another linked project, which is virtual vehicle, where they show also how to assess the driving function using physical targets. I think this scenario is quite interesting because it has been shown how this was done in virtual tool, in driving simulator, but also in the physical wall, let's say at the proving grounds level. Here we can also see another of the linked projects from IDIADA, where we can see the complexity of controlling this kind of dummies that are used for testing purposes, and we can see how the logistics are quite difficult. No? Okay, that's why it's quite important that with the other test methods, we can reduce the number of test cases in order to do the test coverage more efficient in terms of cost and time. And here we can see another scenario where we want to show how the traffic jam chauffeur system is capable of maintaining the vehicle in the lane, and also to work properly when there are cut-ins or cut-outs scenarios. Lastly, we have the last test method. This test method is one of the most is the most different one, okay? Because basically in that case, instead of reproducing a scenario that has been previously defined, what we do is to go in OpenRoad and we look for scenarios, and then we assess that those scenarios are working as expected. In that case, one of the challenges for this kind of method is to have a criteria for defining a route, okay? Because we need to define a route which is interesting for the ODD of the driving function under test. And also
2 more minutes.
Okay, and yeah, okay, so last is to talk about field testing, which also is having 3 main parts. First is to define the route, then execute the test, and then to evaluate. And in that part, I would like just to remark that has the complexity of you having a large volume of data that needs to be analyzed instead of having just a scenario to be evaluated. And here I would like just to finish with some of the linked projects where we can show this part of the methodology. Okay, so for example, this one is the prototype or the system from Virtual Vehicle, where they show how a highway pilot function is working in the highway. And next thing is about the Ensemble project, where the platoon was executed. In that case, it's also important to talk about license exemptions, because we are talking about a fleet of almost, I think, were 7 trucks, and here it was a challenge, to obtain the license exemptions in order to do this kind of test in the public roads. And lastly, I would like to share the 5G Carmen project, where the connectivity was assessed. Okay, in that case, I think it's quite interesting that when we do field testing, we take into consideration this K-enabled technology, because in that case, we need to define routes which are challenging for the connectivity point of view, and not from the, let's say, driving function point of view, which is the normal requirement. Okay, so I would like to give the word to my colleague, Nicolas, in order to explain about this.
Yeah, thank you. Just a few more words on 2 slides. So the first one is formats and interfaces, which is very necessary to us, that there are common interfaces and data formats to combine the international approaches, tools, and methods. So as you have seen in all the presentations until now, is that we use a lot of different tools and databases, and that is necessary because each tool has its advantages, and each database has also its advantages. So therefore, it is necessary to define common interfaces to interact with all the different tools in the open world. So for the scenario description, we defined a few formats. So we did not define them ourselves, but we defined them for HEADSTART to be used as standard. And these are OpenScenario, OpenDrive, and OpenCRG. OpenDrive, I think it is well known, as well as OpenScenario and OpenCRG. OpenDrive is for a static environment. OpenScenario is more for the scenario, and it is maintained by the ASAM consortium, and it's an open standard. We highly recommend to use these open standards. For the simulation and testing, we identified Open Simulation Interface to interact with different parts of the simulation, with different models, and functional mockup interface, the FMI and functional mockup units, FMUs, to integrate models into the simulation, which are also open standards. And finally, for measurement data, we identified the Omega format from the VNV Methods project, which is also an open format, and which is about measurement data. So it is not so much OpenScenario, OpenDrive, but it's more about measurement data from the real world to be integrated into scenario databases, for example, or to be integrated into other tests. So this is for measurement data. And could you go please to the next slide? Yeah, and for the final slide will be the open issues and conclusions. So as I said, the different databases with different scenario concepts are there, and we need to unify data formats, interfaces on an international level to work with various national databases initiatives and to bring everything together. Because if we have 100 times 45,000 kilometers, it doesn't bring us to the goal. But if we combine them, then we have a lot of kilometers already there. Then the exposure and classification of scenarios is not yet unified, which is definitely an open issue for us. Then we have the arbitrary simulation environments, and we did a lot of unification and harmonization in HEADSTART, but there are still open issues in the simulation environment to unify test environments with the focus on simulation, like models, the toolchain itself, interacting between different specific tools. So this is quite an open issue. And then the dynamic allocation of scenarios during the test. So we looked into the allocation of scenarios before the test, but we also identified that there need to be methods to decide on the validity of a test run and automatically allocate accordingly to a more realistic test environment or to a different test environment. And therefore, to provide a safety assurance framework to include relevant national initiatives is necessary. We did a lot of harmonization in HEADSTART, but there are still some open issues which need to be tackled, and they are also mainly focused on reaching consensus in the EU, but also internationally. Okay, thank you. I think now we can go to the questions, Itze.
Yes, indeed, Nicolaas, thank you. Indeed, I want to invite Xavier and Bernard also to join in this question round. So let's start with you, Nicolaas. You showed the methodology in full, and it seems quite an elaborate methodology. There's quite a few steps. So in the end, does it cost more time to do this, or does it save time? How does that work for an OEM or any assessment agency that would want to use this?
It's a good question. I think it is not about saving time or not saving time. I think it is about homologizing and to ensure the safety in general, because there is just no other methodology. So if you look into driving around in a real world, of course it saves time, because you would have to drive around billions of kilometers, which takes a lot of time. So in these terms, yes, it is to save time, but I think there's just no other option except for maybe other methodologies from other projects which we analyzed and put into this harmonized methodology here in HEADSTART.
So that really is an important point, because if you say there is no other option, then this is a topic that really will gain traction in the field. Yes, and another question, you presented on coverages. So the coverage at 3 levels for the testing. So does that mean that we now know when we have tested enough?
I think there are still some open issues. We identified that we need to know how much we tested, but we still need to look more into the details of the 3 different coverages, and especially how much we tested. Highly depends on the specific scenario database, on the underlying framework. So I think we need to look more into details in the future of the different interfaces of the different databases and frameworks.
Okay. Then a question to Xavi. It was really nice to see all the video material of the linked projects and the testing taking place. It becomes really tangible then. So thanks for that. So Xavi, the testing that you showed, is it different than the testing that's already going on in industry?
Yeah, thank you for the question. Yeah, the main difference is that for traditional or classical methodology are following more a kind of waterfall approach, where we go from software testing, system testing, vehicle level testing. And this means that in our methodology, we need to have this kind of test methods already available, because what we need is to test the scenarios, and those scenarios will have a selection and a strategy for each by using all the levels of testing, let's say. So that's why the main difference, I think, is going from a more waterfall approach to a more scenario-based approach, which means to have all the test methods available as soon as it's possible.
So the scenarios are actually the connection point between all the test methods, and you use them in parallel, or much more in parallel than traditionally done, if I understand correctly.
Yes, that's the point.
Yeah. Okay. I want to remind the audience, if you have questions to Nicolas, Bernard, or Xavi, just raise them in the chat box. Then if we go to Bernard, so you showed this process of scenario selection and allocation. So why is it so important? What would go wrong if you do this in the wrong way?
So just looking at the scenario selection part, I think a risk that I see is that the ODD is not sufficiently covered by the scenarios from the database. Because the big risk is this could lead to the impression that automated driving function has passed all the tests and is ready to be approved for traffic, when in reality some parts of the ODD weren't tested at all. So I think this is the big risk here. You have to make sure that really everything from the ODD is covered by the scenarios. So a big emphasis should be set on this part of methodology.
Okay, so it's again coverage of the full ODD. That's key in this. Okay, thank you.
Thank you.
For the audience, we have one more poll for you, a question, and let's launch that. So if we talk about testing and validation, the question is, if we look at full vehicle validation, how much of the work actually in the V cycle is going into the validation? So is that a low level? Is it 1/5, 1/4, 1/3? Please let us have your votes. There's a very nice response there. Thank you. I'll give it 20 more seconds. Okay. And close. And we share it. And what you see is that most of the attendees say that it's 1/3 to 1/4 of the full effort in the V cycle. So that's really considerable. And if I can add to that, I think that with the advent of automated driving, it's only becoming more. And that's what makes HEADSTART so important in this scenario-based approach. So thanks for this. We will have a short break now. We will get back at 10:45. And thank you for attending. After the break, we have nice presentations on the users of the HEADSTART methodology, the use cases, and the key enabling technologies. So stay tuned, and we'll be seeing you back at 10:45. The HEADSTART webinar and the HEADSTART final event. We are starting the second half of our presentations now. And the first speaker will be Jacco van der Sluis of TNO. and he will be introducing the use cases that we looked at and how the HEADSTART methodology could be applied. So Jacco, please go ahead.
Yes, thank you, Sietse. Thank you for the introduction. So this session is on the 3 use cases we have identified in HEADSTART. The first one is truck platooning. I will also show some slides. And for the highway pilot and traffic jam chauffeur, I will combine the slides. The idea is that after this presentation, we have identified how suitable the HEADSTART methods are for the 3 use cases. So if I start with the truck platooning use case, and we can already make a general statement saying that it's a very good use case. As mentioned before, we identified V2X communication as a key enabling technology within HEADSTART. And well, truck platooning is a very good example of a real cooperative applications where you have interaction supported by V2X communication. So when you take a focus at V2V communication, what will be exchanged between the vehicles, then you have information sharing at operational layers where you have, say, for instance, the data you need for your vehicle control systems. There is tactical information for instance, keeping the platoon together, and also some strategical data will be exchanged. So that is less real-time data, for instance, looking at information from what is happening at the local traffic situation, or information related to route planning. That kind of data will be exchanged also. And another part is, well, the communication with infrastructure. So that's bidirectional. And how can the digital infrastructure support the platooning application? Also, if you look at truck platooning, the V2X communication is really enabling the automated driving function. So yeah, at vehicle level, this is again operational data to support the ADAS functions, for instance, for lateral control, lane keeping, etc., that kind of information. But really, if you look at more the tactical level, so it's a combination of operational and tactical data at platoon level, where you need to share that information across the members in the platoon to really, enable the platoon maneuvering, have some coordination when a vehicle wants to join the platoon, and also when you are platooning, for instance, in a highway setting, how can you keep the platoon together? So that is, the information you need to exchange amongst the members to keep cohesion in a platoon. So it's a good use case. That is an overall finding, of course, but also it's a very complex use case. So if you look at vehicle level, you need already a lot of onboard platforms. So it's really a system of systems at a vehicle level. But if you zoom out a bit at platoon level, it's already a system of vehicles. And another thing could be, okay, we can have a monobrand implementation that, if you add another layer of complexity by, for instance, putting a focus on multi-brand platooning, where you have, all these OEM-specific solutions which should come together. So in that sense, Ensemble is a very good example of multi-brand platooning, and that was also a linked project to the HEADSTART project. And another thing is that the scenario-based assessment, really helps in handling such a complexity. So we have, complexity at different levels. But if you look, for instance, at the platoon maneuvering and interactions which are there, there is a good fit to get it into the scenario. So it's a very practical approach also if you have high-level platoon maneuvering. So in the figure on the slide is an example of some of the, say, defined platoon maneuvers. It really helps to get it into, for instance, scenarios related to platoon engage situations where you have a vehicle joining the platoon, and also for the normal platoon maneuvering, where you can have scenarios dedicated for the nominal platooning, platoon cohesion, but also in relation with gap adaptation or stop and go. So it's very useful to fit that into that scenario. Another thing is that by default, V2X communication will also be a part of the scenario because it's a main enabler for the platooning. You really need the communication for a vehicle which wants to join the platoon. It really needs the communication function to be able to do that. Another thing is that V2X communication, it can also be safety critical. So that may be a bit less applicable when it's really strategical information, but if you have the time critical information like the operational data you need for vehicle following, for instance, then the V2X communication also becomes a part of the safety critical system. And it's also very useful to introduce V2X failure modes into the scenarios. For instance, you need the V2X communication to enable the platooning and maintain the platoon. But what will happen, for instance, if V2X messages are dropped? So it's very interesting to investigate that kind of scenarios. How will the system handle such situation when there are some communication failures? So that's very useful. And another thing to mention is the usability of scenarios. So it's very easily to derive some generic truck platooning scenarios, which you can then reuse, for instance, across testing methods. So the scenarios you use in your virtual testing setup or in your hardware in the loop setup, you can also use that kind of scenario or similar scenarios at your proving ground. So that is very useful. And also in the sense of what am I assessing? Are we assessing a truck platoon with 2 vehicles or with 5 vehicles? For a joining scenario, you can still use the same scenarios in that situation. Is it a mono brand implementation you are testing? Yeah, you can still use the same join scenarios also in a multi-brand setting. So in that sense, there is a high usability of the scenarios. So one more final slide related to the truck platooning use case. So I think what we find out is also that the technical readiness level of platooning also has some impact on how we can apply the HEADSTART methods. So of course it's still highly in a research phase. So we cannot get the scenarios out of existing scenario databases. Also looking at scenario selection and allocation, it will highly depend on expert knowledge. And I think that goes for also other blocks of our methods. It highly relies on expert knowledge. Also, if you look at Ensemble, where they worked on multi-brand platooning, there they are still in the phase of defining pre-standards for, say, the messages you need that being exchanged in a platoon, and also developing a platooning protocol. It are ongoing activities, so no standards for testing are available, and you already get quickly in a situation where you are really looking at solution-specific implementations which are being tested. And of course, we already showed some videos where we had platooning on proving grounds, but it's difficult, of course, to deploy platooning on public roads. So also for the demonstrations of Ensemble, they needed specific exemptions to do that on the roads in Spain. So to quickly sum up, so it's very good match for scenario-based assessment, and also looking at the 3 identified key enabling technologies. Yeah, they all apply for the platooning use case. So with that, I want to start with the combination of the traffic jam chauffeur and highway pilot use case. So here also, if you look at say the connected automated driving application itself, yeah, the high accuracy perception systems are needed. So for traffic jam chauffeur at low speed, and for highway pilot, of course, also for the highest speeds which you will drive on the highway. So you need to properly detect, for instance, traffic jam situations. Perhaps you need to extend the sensors on board, so you really have complete coverage. And yeah, like I explained before, we combine these 2 use cases because yeah, they are a bit comparable for some of the evaluations we do in these slides. But yeah, at least for highway pilot, yeah, there are some difference in the ODD, of course. If you look at the positioning systems, also you need really high accuracy positioning systems to enable also to be the HD maps to be used as sort of a sensor for instance, speed limit computations, but also when can you then activate such systems, or for instance, for identifying the next highway exits. V2X communication can also play an important role where you, for instance, have then support from the digital infrastructure for identifying road hazards or road hazard warnings, standstill vehicles, etc. These kind of situations. And also, if you look at the regulations for assessments, yeah, ALKS regulations. Yeah, they will be addressed in some upcoming next sessions related to key use groups. So there will be more details on that shortly. So also here, the scenario-based assessment really helps the complexity in these 2 use cases. And if you look at the ODD for traffic jam chauffeur and highway pilot, there is already a good scenario coverage. Of course, we already heard some remarks about being complete. That is still, of course, an attention point. And also the ALKS regulation is also defining scenario catalog for this. Here also the positioning by default is part of the scenario, where you can also have lane detection relying on HD map. And also I think it's important to have some kind of assessment of the positioning performance, where you have specific scenarios which you need to have to really have a good feeling about the performance and if the accuracy is appropriate. If you look at yes, thank you. If you look at usability of scenarios, so maybe you don't need a huge number of logical scenarios, but for instance, if you look at the sensor set you have on board, or if you look at the slow speeds or really the high speeds you have at the highway, you will have a large number of parameter variations. So in that sense, virtual testing can already help you in that sense. And also, vehicle in the loop can help you, for instance, for validate different corner cases where you can look at, okay, maybe it's unsafe to execute it at a proving ground, and vehicle in the loop can already help with that. And also here, like in truck platooning, you see that scenarios can be reproduced from virtual environments, from sil-based environments to proving grounds. So I will not talk about all this because the time is up, but what you can find is scenario base are already available. Also, you will need some expert knowledge for scenario selection and allocation. And if you look at the level 3 systems, that will also have impacts on scenarios. The redundancy you perhaps need in these kind of systems. The ODD, which could change and could lead in if you really take the single lane situation and you go to multi-lanes, scenarios will increase. Good thing also, current many OEMs are already looking at their L3 systems for homologation. So I think for the key enabling technologies, it's very suitable, of course, for the positioning system, but also in relation with communication V2X. So,
Okay.
Thank you.
Jacob, thanks very much. I have one question for you because you showed 3 use cases now. And so if you look and you looked at how suitable the methodology is for them, if we take a wildly different system, so let's say bicycles or tractors in the field, would the methodology then still be applicable?
Yes, of course. When you look at the methods we use, we start, for instance, with the scenario database. Of course, it depends a bit on what is available. So in that sense, it's also related to scenarios with where can you get the information from, how does the expert knowledge relate to that kind of scenarios in allocating the correct scenarios. But for instance, if you look at the previous presentation where they talked about the different layers which you need and what kind of information you will need in that scenarios, as long as you can fill in these kind of factors, you can apply it in that sense.
Okay, so the methodology stays the same. The expertise, it may be different, and maybe the data needs to be different. Okay.
Yes, exactly.
Okay, thanks, Jacco. Then we will move to the next topic, which is key user groups. So who will be using the HEADSTART methodology? And the first speaker is Oriol Flix of Applus Idiada, and he will talk about approval.
Okay, just a second that I'm showing the correct screen. Okay, I guess that everything is working.
Yes.
Okay, now my camera. So sorry for the mess, but I'm waiting for a COVID test, so that's what happened right now, and I will have to talk in this way. So yeah, we will give a presentation on the key user groups, that the work that we have doing in the HEADSTART methodology and the HEADSTART project. And together with me, Oriol Flix, we will present Andreas de Canella and Jeff Van Montfort. So first of all, I'm going to give the explanation on the approval side of the HEADSTART methodology and the key user groups. And we are going to give a brief introduction on the type approval for these people that is not related to the type approval certification procedure and so on, and how it can be related with the HEADSTART. And then we are going to give an example with one of the most important systems that now are related to the automated and connected vehicles, that is on Regulation 157 for automated and lane keeping systems. So entering on the type approval side. So type approval means the procedure whereby an approval authority certifies that the type of vehicle or a component or a system that will be fitted on a vehicle satisfies the relevant administrative provisions and technical requirements that has been defined by the authorities and all the stakeholders that are relevant for this. So in this case, the manufacturer provides, together with a prototype and the documentation that defines the system that is going to be approved, to a technical service or approval authority. These technical services are testing the system according to the requirements defined in the regulation. This provides with a report that defines that you have fulfilling all the requirements and is sent to the approval authority that, on behalf of the European Commission and the regulation 2019/858, says that this system can be sold on the market, where it enters the HEADSTART methodology. So at the first processes of the type approval, where the manufacturer defines with documentation how this system has been assessed and the description of this system and how it's being tested by the technical service. After that, so who defines these regulations? In Europe, most of the regulations are defined by the United Nations Authority, and this is under the scope of the World Forum for the Harmonization of Vehicle Regulations. Inside of this World Forum, there are several expert groups, but the most important for us is the GRVA. That is the one that is defining the requirements regarding all the automated and connected vehicles. Inside of these groups, HEADSTART and also other methodologies are taking a lot of importance, and also we have performed some presentations inside of these expert groups because they want to know how to assess and how to perform these new validation methods for all these systems that are related to connected and automated vehicles. After that, if we're entering to the regulation 157 for the automated lane keeping system. So this is the first regulation related to SI level 3. So we take into account that it's a system that has the main responsibility of the driving, while the driver is not the first responsible, let's say, of the actions. And while in the last approach of the certification, the homologation started before selling the vehicles to the market, now we have to ensure that during the development stage, the manufacturer has followed some processes that are validating all the safety and the security of the system during all the development phase, the V model, let's say. And the important part here is that the HEADSTART methodology is very useful and can cover also this stage performed by the manufacturer, but part of this stage that will be together performed with the certification authority or the technical service. So we are partners of the manufacturers in this stage. So the HEADSTART methodology can provide an output also for the homologation and authorization. How? So as I said previously, we focused a lot on all the systems and so on with the physical certification tests in the proving ground. So we wanted to assess through testing that the systems were safe enough. But now there is an important part that it's called the three-pillar approach, that is the base of the certification or the assessment of the safety, that is called the audit or an assessment. This takes into account the development process of the system, okay, and the assessment of the safety concept. So also an important part that is related to that is that we can use the simulation results provided by some scenarios and some testing in hardware in the loop and so on that has been performed by the manufacturer, and this can be used for the audit and assessment that we will perform firstly in the certification. Okay, so after that we are going to perform the physical certification test. That is something that is very common, and a little part related to real world test drive. But again, the HEADSTART methodology can cover the biggest part of the certification procedure together with the development phase performed with the manufacturer. So, for example, in Regulation 157, this is a system that controls the lateral and longitudinal movement of the vehicle for extended periods without the need of further driver input. As I said, this is the first SI level 3 system. and is only for M1 vehicles. It has also some ODD constraints and limitations. So basically, the system can be used only in highways and under speeds of 60 kph. Inside of these regulations, we find a set of requirements that can be divided in 5 aspects. First of all, to evaluate the safety and fail-safe response of the system. After that, human machine interface, where the driver has to be aware of if the system is working or not, basically. Then object and event detection and response, more related to radars and lidars and sensors that are used by the system. Data storage systems for automated systems. That means event data recorders and so on. So the vehicle has to record if the system is working or not. And finally, cybersecurity and software updates. Here, where we can use the HEADSTART methodology. First of all, in the cybersecurity part, because it's one of the key enabling technologies. So part of the methodology used can be provided as technical documentation to the technical service in order to assess that the cybersecurity has been taken into account and it's correctly implemented inside of the vehicle. And as we said, the biggest part is related to the safety and fail-safe response, where part of the simulations performed with scenarios that has been created by the HEADSTART can be provided to the technical service, and we can assess that part of this system is safe enough for the specific test cases. Why we can use simulations? So that's something that cannot be used in all the regulations. It's something that has been introduced for all the connected and automated systems that are being developed by the United Nations working groups. And here, for example, inside of the regulation is where it is defined that we can use general simulation programs in order to assess the performance level of the vehicle. In this case, it is also defined which kind of simulations we can use. So, for example, the cut-in scenarios, cut-out scenarios, and deceleration scenarios. Of course, this will be covered by the HEADSTART methodology, implementing the different layers and assessing which scenarios are more relevant for the specific system in order to assess the final safety of this vehicle. After that, we will go to the proving ground, where some test cases are also defined regarding the lane keeping, the collision avoidance following a lead vehicle, lane change of another vehicle, stationary obstacles after the lane change of the lead vehicle, and finally, the field of view test. Here also, we can use the HEADSTART methodology as a technical service in this side in order to define which scenarios can be selected for each of the use cases in order to assess better the safety, the part that we have previously assessed with the simulation, but we want to ensure that in the proving ground, in a more controlled, safer area, we can assess better and have a final verification of these test cases and these functions. So now I will leave the floor to my colleague, Jeff van Montfort, that will talk about the consumer testing.
So Jeff van Montfort, as announced, will continue on the consumer testing.
Yeah.
Please go ahead, Jeff.
Thank you, Oriol, for the presentation on approval. I will present consumer testing, and later on I'll also present the technology developers section. Oriol will be in control, so I'll ask Oriol now to go to the next slide. Thank you. Yeah, so to put it in a bit of perspective, a short introduction to consumer testing. So the consumer testing organizations are there to provide information to the normal consumers on the safety of vehicles. So in general, they go beyond the legal requirements for the safety in that region. If you look worldwide, there are about 10 of those. The most known ones are, of course, your NCAP, but also in the US, IHS, US NCAP, and in Asia, several like JNCAP, KNCAP, and China NCAP. To keep it a bit simple, we use your NCAP because they are quite exemplary for the progressive consumer testing worldwide. So the ones that are really look into the most advanced systems that are being brought on the market, so also with the higher level of automation systems, as well as the more advanced ADAS systems. So you can go to the next slide. So what does EUR-NCAP currently have in their safety performance assessment? If we look at active safety, there are three components that they have. They have the standard star rating. I think you all are aware of that. That's a star rating that a vehicle can get. There, the focus is really on the assessment of ADAS emergency systems. So, for example, AEB and lane departure warning systems, but really with the focus on emergency, so less on comfort. This is done largely based on physical proving ground testing, which is combined with OEM predictions and information. You see it on the right-hand side. On the top left, that's, for example, the prediction that the OEM has to provide of a whole kind of grid where the parameters vary. Every cell is an individual test of a scenario with specific parameter combinations. Those are then tested, and not all of them are tested by EUR-NCAP, but part of them are tested by EUR-NCAP, and they give kind of a correction factor to see how well can we trust the provided information. Here you can already see a large set of tests that is being done. You see some in darkness with a pedestrian, you see some with lines, you see others with moving other vehicles, even a turning one. So it's quite a large variety of scenarios that is currently being assessed already with the star rating. But again, this is all ADAS emergency. If we then go into a bit more complex ones, there is the assisted driving. This is done via the assisted driving grading, and currently this is all based on highway assist systems. There they have the approach of combining assistance competence, vehicle assistance, and safety backup. And again, this is largely based on physical proving ground testing performed by the EUR-NCAP labs in combination with information that is provided by the OEMs and predictions and information. Then the next steps is if we really go from assisted to automated, for example, ALPS systems. They are yet to be detailed because they're currently not on the market, but this is expected to have a similar approach, at least for the short term. Okay, go to the next slide. So the reason I just showed you previously is just to indicate that there is already quite a set of tests to be done on the test track, mainly some in the field, but it's a bit on the edge. So in order to extend EUR-NCAP and also other consumer testing wants to assess a larger test suite. On one hand, a larger variety of scenarios, so with more different configurations, like different objects that are encountered, perhaps multiple objects, these kind of things, but also more scenario parameters with wider ranges. So you can also imagine that there are other types of vehicles, but also in different positions, with different speeds, with larger speed ranges, these kind of parameters. And all to address either more emergency cases for the ADAS systems, so the ADAS emergency systems, or even go into a larger ODD for assisted driving, or even inclusion of automated driving. In order to do that, you are almost forced to work with a scenario-based approach. And in order to control cost and duration per series, the inclusions of other test methods than purely test tracks are required. Given this, then, if you can go to the next slide, this is where also HEADSTART will come in, because this is actually what the HEADSTART methodology can really well facilitate. And as already shown by in several presentations earlier on, this is really the core of HEADSTART. And also, if you look on the left side, that's a picture from the working group, the virtual testing EUR-NCAP working group, where you really see on the most left, it's like we need a kind of a scenario database. So there needs to be sources of the databases that then can be allocated to different types of testing. That's the central column, which is also very similar to what we have at the HEADSTART side with the different test methods. This then needs to be combined to get an assessment, but also to ensure that the correlation and validation of the different test methods is reasonable. So can, for example, the simulations be trusted, or the vehicle in the loop, or the proving ground even? How well do they correlate? Yeah, if you look at the HEADSTART methodology, it has the very similar components, and the further details that are made within the HEADSTART methodology, for example, on the format, that is very relevant and very applicable to for your NCAP. So this is a bit in a nutshell why the HEADSTART methodology is very relevant, and it is actually brought into the Euro NCAP working group by several partners from the consortium, but also from industry, because several of the HEADSTART partners are Euro NCAP lab or representing Euro NCAP members, but also industry is represented. So that's a very nice way that we can use the HEADSTART methodology for your NCAP and also for the other consumer testing organizations. So thank you. So that's on consumer testing. You go to the next slide, please. So this is on the technology developers. So really looking into it from the side, like what are the specific requirements and consequences of it if you are making those systems. Andreas Tacanella created the slides, and I will present them briefly to not switch too much. Here, it's more from a technical point to create the systems. And what you see is if you go from L2 to L3 and even L4, a new architecture is needed, because a few things. The bigger responsibility of the car manufacturers, where it's not just the driver that has the control, but it's more also looking into the driver, passenger, and other road users, because the vehicle is being driven by itself, so not by the driver anymore. So there's a bigger responsibility. Also, it requires a more complex architecture, because new standards and new homologation procedures are needed because of the change of driver task, which was previously with the driver, but will be now with the vehicle. Also, in order to be able to facilitate this, communication is needed and is required, because you, for example, you need to know better what's your position in lane, but also vehicle to vehicle or vehicle to infrastructure communications really can add to further improve safety and are needed to facilitate the level 3, level 4 implementations. If you go to the next slide. So if we then look at, for example, the sensors, to show a bit about the complexity increase, if we go on level 2, it's in general one or multiple of the standard sensors that are used, radar, camera, ultrasonic, but also the a priori perception sensors like the standard GNS and cellular connectivity. But those are the quite relatively simple and require less interaction. But if we go to the L3 systems, more complex sensors are needed, combinations of sensors are needed, and even perhaps the addition of, for example, LiDAR is being used to further be able to have the perception level or the perception system correct and accurate enough. But also the a priori perception sensors are more complex, because you need to get, for example, to a higher definition positioning, but also, as mentioned already previously, as an example within Ensemble, the communication is very important. Because if you start working cooperative, the communication is essential, but even before that, if it's a one-way, for example, getting information from infrastructure, that is of course also very relevant, but requires a different type and a reliance on that information. You can go to the next slide. So what about the new challenges that it brings? I will very quickly run through. So it's about the statistical demonstration of the system, but then without the driver interaction. So that's a full autonomous system. But we also know that there are interactions with the driver, so there is still the driver in the loop. So that also needs to be taken into account, especially, of course, in cases of takeover requests. and how does the system handle that? So that's a complexity, an additional challenge. But also how to handle scenarios that are currently not known in traffic. So how can we anticipate on that? What kind of scenarios do we know? But also we somehow need to facilitate the possibility to get new scenarios, and perhaps new occur because of the AD functions that are on in the vehicles. Then also the configurations and the different variants need to be taken into account, things that can change over time, but also, for example, failure or damages, things like that need to be taken into account. And then a fifth point, those systems very likely will all rely on machine learning. And how can that be included? That's really a big challenge for the future. If we then look at those challenges on the next slide, where does the HEADSTART methodology support the challenge that we're just mentioned? So the first one is really the creation of the scenario database really will help. We can really from a scenario database, the real world information can be used there. We can learn about what are the parameter distributions, how are the variations, these kind of topics, but perhaps also with upcoming new scenarios. On the block 2, there we can use we see the injection of the three HEADSTART key enabling technologies, where in particular the positioning and the communication are very relevant and are very interesting. That's where you can include those to also, for example, include failures. Then the results of the different test methods are very interesting. So the combination of the virtual testing, skill-based, proving ground testing, and the field testing, they can all play their role. So that's very relevant. And of course, the assessment at the end, where we can have pass-fail reports with the ODD limitations. And also you see a feedback loop from the evaluation back into the databases, where we can feed in the information and further improve the databases, but also, for example, feedback into the selection and of the scenarios and the allocation. The fifth point I earlier mentioned on, it can help the scenario-based approach from HEADSTART for machine learning, but I think other things are also needed, and that's also why you see that several dedicated projects ongoing and being developed to address that in particular. Thank you. That's the next slide. This was my last slide.
Okay, thank you, Chef van Montfort. I have two questions for you and Oriol Flix. So the first to Oriol, you spoke about approval. So does that now mean that a vehicle will get a HEADSTART stamp or a HEADSTART approval? Does it work that way?
We will like. No, the thing is that the HEADSTART methodology can be part of the approval procedure. Okay, so this HEADSTART methodology will help the technical services and the approval authorities to assess the safety of the systems in a better way. Okay, and part of this procedure is a procedure that will be performed by the manufacturer in the development process, and this documentation and these outputs and results that we'll get on this development process will be used by us in order to assess the safety of the system or the vehicle itself.
Okay, clear. Okay, thanks. Chef, and you talked about consumer testing. So will HEADSTART now help to raise consumer acceptance and trust in automated driving?
Good question. By itself, I don't think, because the methodology itself, I think that's too complex to explain to normal consumers. But it definitely will help to do it in a very structured way, which also makes it easier to explain to consumers. So there will be an additional layer needed to get it really explained to the consumers, the different types of testing, things like that. But it definitely will help to structure.
Okay, Thanks, Chef, for answering that. So we move on to the next big technical block, which is on key enabling technologies. And the first speaker will be Joachim Castello-Triginer of Virtual Vehicle, and he will speak about cybersecurity. And it's probably more than just phishing mails. We're talking about cybersecurity of cars here, of course. So please, Joachim, go ahead.
Okay, I hope you see my slides.
Yes, we do.
Okay. In this last part of the final review meeting, I'm going to introduce cybersecurity as a key-enabled technology, and then Andrea will continue it with the other two key-enabled technologies. My name is Kim, and together with Athanasius, we introduced this cybersecurity key-enabled technology. First, I want you to put you in context. The key-enabled technology, where is allocated in the methodology, and this is the part of the CATS. Here you can see as well for cybersecurity, and that was part of the enhancement of this methodology introduced in this part. And what was done here was in this enhance of the parameters by introducing different parameters, distribution, and stochastic variation that further Andrea will introduce. Okay, but here we have the first problem, or when we start to struggle in cybersecurity. So we, by the beginning of the project, we include cybersecurity as well key-enabled technology, but we really didn't have specific parameters or specific distributions and connected, for example, to physical variables that we could really make profit for cybersecurity. Therefore, we translate that into different test allocations, and we start to split key-enabled technologies by introducing as well another specific cybersecurity assessment in the methodology. This specific cybersecurity assessment was, the plan was to enhance or to complete the different cybersecurity tasks that we should perform in order to validate safety connected automated driving vehicles. Then we move to the procedure, and here we had our specific cybersecurity branch, and this specific cybersecurity branch could put or allocate those tasks that was required for us in order to evaluate cybersecurity. In this part of the branch, if you zoom in a bit, what we did was to use a well-established approach on IT that was this common criteria and adapt to HEADSTART and try to build a framework where we could, let's say, derive based on the assets that were relevant for testing, derive some tests connected to those requirements that are specifically for cybersecurity. In that sense, the approach of the common criteria that we use to adapt to HEADSTART as well provide two other benefits, and one was the inclusion of all the user groups that we represent in HEADSTART, and at the same time it provides an evaluation assurance level that could provide as well rationalities and specific values in order to assess and to know how deep we went into analyzing cybersecurity. So we could have this framework, and it was the framework that we select for HEADSTART. And then we wanted to go further into this application and demonstration of this framework. And here we struggled. We struggled a bit because within the consortium and within the use case selected and those linked projects that were associated on those use cases, we could not find really truly cybersecurity oriented projects. And at the same time, if there was, for example, if you're talking about communication, there was a security. It was not it was in the early stages, or was not fully developed for cybersecurity, which means that we could represent other key-enabled technologies, but we lack on this cybersecurity representation. We work on two specific projects. First, we try to work on Ensembler. I think that already Jaco talked about Ensembler, and it's well known that this is this multi-brand factor tuning. Basically, it was connect with communication as a key-enabled technologies in this part of the application on demonstration, but was not built for cybersecurity. And here we tried to cooperate with Ensembler, since they already, while implementing, consider cybersecurity for this security framework, but was pure technical oriented on technical level, and there were a lack of security by design. So at the end, it was for us a prioritization of this communication key-enabled technologies to use this link project. Later on, we had this BNR consortium that they had this RISE self-driving model vehicle platform, and that was used to demonstrate the adoption of the test procedure in HEADSTART methodology, and as well to allocate these different test cases for traffic type repair based on this advanced line keeping system, a regulation. And it was, for one side, really valuable, this platform. But on the other side, they already went through cybersecurity, introducing this black box testing for security informed safety. And there were introducing an approach where they could test, in this case, this positioning and the property of availability, and they could in somehow provide this approach. And this, let's say, approach was as well really well defined, and it was giving us an option to cooperate together based on the HEADSTART procedure. And that's what we did in that stages. We could compare their approach with our procedure, and we could validate the different steps that they could do and figure out which were and somehow parts that could be enhanced, or for both, not just for this approach as well for HEADSTART. And that was what it happens at the end. So for one side, they had this attack catalog include on that could really help to test cybersecurity requirements. And that was the next step that we didn't go in HEADSTART. But at the same time, in our approach, we could integrate more different target groups, and at the same time introduce this kind of assurance level criteria that we could work in HEADSTART.
You have 2 minutes left.
finally, in order to assess or to validate, let's say, the methodology, we went through the state of art, and we went again to see what the other projects were working, and we went through these L3 pilots best practices, where they defined best practices for cybersecurity, and we went through the document and see what HEADSTART was missing or what already considered HEADSTART. And we, let's say, successfully saw that there was a lot of principles that they were introduced, and that with this specific, not just adaptation in the CATS for cybersecurity, with this specific cybersecurity assessment, we could cover different topics like security by design, or those requirements, cybersecurity requirements, or this management on the vehicle level of the threats that can vehicle have, and that leads again to realize the achievements that cybersecurity did in that project. That was this adoption of the common criteria in our procedure, to have our own cybersecurity assessment separated but integrated at the same time. And we had this as well, threats on the vehicle level and cybersecurity requirements. And more, we had this HEADSTART assurance level that was presented for a specific communication head. And well, this is my last slide. Finally, we could conclude that cybersecurity key-enabled technology, I see in HEADSTART a seed to go towards this scenario-based approach integration, and there's more steps and to do and to go further into that. As well, we could integrate different user groups that was really beneficial, and we could introduce this HEADSTART assurance level for the communication. And of course, there are a lot of points where can be enhanced or cybersecurity, but probably we could jump into the questions later on.
Thanks, Joachim, for your presentation. I see with the HEADSTART assurance level, we will get a HEADSTART stamp after all. That's very nice to see. Because of time, we move directly to the next speaker, which is Andrea Stecanella of CRF in Italy. And he will talk about positioning and communication and V2X. So please, Andrea, go ahead.
Yes, you should be able to see my screen now.
Yes.
Okay, perfect. So let's move to the positioning and communication CATS. The presentation has been made by me and Jaco from TNO. The main point I would like to discuss is that we have several applications that might benefit from positioning and absolute positioning and V2X communication, no matter the way you do that, but the point is that we are open the way to new possibilities. And in HEADSTART project, we are working with, in particular, with two public funding activities, like the 5G Carmen project, where we have developed a cooperative lane merge system. And of course, we already talked about this, but there is also Ensemble, where we have the platoon formation enhanced by V2X communication. So in both these two projects, we have implemented a system that is able to trigger new maneuvers based on digital information. More in details, knowing the position, the lane level position of the vehicles, it is possible to coordinate the maneuvers. For example, in 5G Carmen, we have opened the gap among vehicles in order to let the vehicles enter. And after that, we will rely on the standard level 2 sensor systems in order to keep the cooperative driving going on. Similarly, in Ensemble, there are several scenarios where you need to manage the platoon formation and the proper driving when the convoy is formed. And to do so, you need to rely on this new field, new channel that enable you to cooperate well beyond the reach of the standard sensors. So the first things we did in the project was to check the impact that this new technology will imply into the development of the autonomous driving functions. So we know that this new channel is very different from the rest, and we have identified several parameters that we should take care during our validation procedure. And the important fact is that this information is lying outside the traditional operational design domain of the car maker, because in order to use this information, you need to rely to systems that are implemented by other actors, like the infrastructure operator or other car makers, which are typically outside the design domain of the car maker. Along the entire duration of the project, we have seen several times some correlation between V2X and positioning, since the positioning is somehow the way you can correlate information, geolocalize information between infrastructure and vehicles, but also between vehicles. So somehow it is like the linking point between also the HD map world and the perception sensors that you already have in the vehicle. But of course, since we are leveraging on digital information, we also have seen several times these dependencies between V2X and cybersecurity. So going into our methodology that we have seen several times so far, we have seen that the impacts of this new enabled technology is applicable to the selection of the parameters that you needed to manage at the validation, even if it is virtual hardware in the loop or in the field test. Then we had some necessity, requirements to introduce this key enabling technology into the allocation of the scenario. So in the virtual validation, you can manage the test with some simulation tools. But then when you go into the real world or also in the hardware in the loop, you need some additional hardware to manage this scenario properly. And finally, we need to somehow compare what is going on in the different allocations, so the virtual, the hardware, and the rest of it. Going in details, these two technologies, so the communication and positioning, should be validated at different levels for many reasons. The first fact is that since we are relying on digital content, the errors or the problems that might affect this technology should be addressed at different levels. Some of them can be simply tested in the real life, in the proving grounds, for instance, but some other problems might occur in very rare occasions. For example, for GNSS positioning systems, you could have failure at the satellite link, and this is very, very rare, but still for safety application, you need to test it. And similarly, you have problems for the V2X communications. So our methodology is somehow working in a loop. So you can start from integrating the technology in a scenario perspective, so implementing the capabilities communicated with other actors. Then you need to perform some single component testing, so you can try to inject problems, errors, failure at component level. But in the end, you need also to go in the real life and see how the system is behaving in real conditions. For example, driving in the city centers where you have many interferences, you have multipath, you have a lot of problems. But ideally, our methodology should be able to record data from the real world, create the new scenario database, and then replicate it again in the simulation, reducing at every iteration the risk of not handling properly some applications. We have seen many examples during the today's presentations, but one important thing in each test is that virtual test is very good at the beginning when you need to define new applications. As we mentioned earlier, we don't have at the moment automated driving function really relying on V2X or positioning for safety so far at level 2. but we will have more and more applications relying on this data in the future, since in level 3, the information coming beyond the reach of the camera or radar sensor is very useful to implement new functions, also safer functions. Not only for triggering the situation, but also to perform emergency maneuver when one of the traditional sensors cannot work. The problem is that since we don't have a standard regulation available, we don't have a real implementation relying on that, we have very few scenario databases, but the industry is moving in this direction because level 3 vehicle is coming, of course. So also the hardware in the loop and software in the loop is very suitable to test the scenarios in a robust way, in a redundant way, and also replicating the test, changing the parameters and the configurations. Still, we have a problem with the hardware in the loop that you need somehow to keep the coherency between different sensors in order to let the data fusion algorithm to work properly. This is already difficult when you talk about a single vehicle. For example, when you fuse the data from the GNSS receiver and IMU, so the acceleration of the vehicle, the dynamic of the vehicles, this will be much more complex when you start to talk about a network of vehicles, so a network of vehicles actors cooperating together. For this reason, we will still need to go in the real life. We need to do the testing. This will assure us the proper function of the application. Also, there are some situations where you cannot simply test the application in proving ground, closed tracks. For example, if you need GNSS corrections, you need a base station around you. This is not granted all the time. Also, you need HD maps, which are available only on public roads, mainly. So we still need the support from the OKR owners in order to have a proper validation. And we are working as the industry, but also in these research activities on the way to do so. V2X for this is a good opportunities because it enables us to share in a common format data information from the ego vehicles and the sensor data in a standard way, in a shared way among the entire industry.
1 minute left.
Yes, perfect. We are at the conclusion. So just to summarize what we did in HEADSTART. So we have tried to do the first testing on positioning and HD positioning and V2X communications. We have seen that the two are strongly connected and they can bring a benefit to the automated driving world. It can be used to trigger, so to do preventive maneuvers, but also to keep the coordination, to keep, for example, a platooning formation. And we know that the simulation will play a major role in this task. The verification, validation of positioning and V2X should be performed at multiple levels, so starting from the virtual world to the hardware in the loop, but also in the real life. And this should be somehow handled from the beginning. So we need to design the system, taking into account these steps. And one last important part is that the design of automated function, especially at higher level, does not end with the launch of the product, but we really need to take care about the post processing of the data. We need to collect information from the vehicles after they are on the market in order to improve the system in terms of reliability, but also to enlarge and create a more robust autonomous driving application that could run everywhere in the world and not only in a very small context. Okay, so that's all from my side. Thank you very much.
Thank you, Andrea. I have one question for you. So you clearly, for positioning, what everybody knows is GPS, and you explained that we are already way beyond just using GPS. So if AD functions now move to urban applications, what will this mean for positioning?
Yes. So, well, the standard solution for absolute position at the moment is GNSS, which is working quite well in the open roads like highway where you don't have obstacles, but for sure we'll move also in the urban where GNSS has more problems to work properly. In this direction, the data fusion algorithms with other sensors will be mandatory, not only in terms of LiDAR or other camera sensors, for instance, but also new technologies will come to play. So I'm thinking about, for example, 5G possibilities, but also a new satellite signals that will be available in the future. So it will come later, but we will have some possibilities also there.
Good, thanks, Andrea. Then we move to the last section of the presentations, and that's on evaluation and conclusions. It will be presented by Xavier Sellart of Applus Ideada. And Xavier, please go ahead.
Thank you, Sitze. Sorry. Okay, so basically that's the last presentation. Okay, so as my colleague Carlos was presenting at the beginning of the event, in the HEADSTART we defined 5 main objectives. Okay, so that were first of all to identify, then to harmonize on the common methods and needs, to define and develop, to demonstrate, and also to reach consensus in the whole community. So basically, what we have been able is, first of all, we have reached the first objective by creating a dynamic catalog of the different user groups, methodologies, toolchains, legislations, and we made a gap analysis, and we at the end had a set of requirements for our methodology that were the base to define the methodology. So, and also the second objective we have reached by transforming this set of requirements by a methodology which has covered all the requirements that were defined in this analysis. So then the third objective we reached by transforming this methodology in a procedure where each of the user groups can understand and can know how are the steps to follow in order to execute this methodology. And also we develop it by using it in some of the use cases defined by the interesting of the interest of the user groups. Lastly, one of the also challenges was also to demonstrate, and basically we have reached this objective by linking some projects where we can demonstrate that the methodology and the procedure was able to meet our goals. And finally, we have performed a transversal activity to reach consensus, in which we have created an expert network engaging different dialogues with the community, with different stakeholders, and basically with 3 objectives. No, we have shown the progress in the different workshops, we have gotten feedback from the experts, and also we have steered where this should go. And finally, there are a list of deliverables already available, and some of them are not yet, but will be soon. And well, the learning of the database of the project are the scenario databases are a key element for SICAM verification and validation, but there is still a lack of harmonization between each other. We need for more harmonization in simulation, and also there are some lack of compatibility between tools in simulation and physical tests. And also we see that the standardization will play a big role in the next years. Okay, so future work is that we must prove to be reliable in every possible driving scenario, and this means to build a strong safety safety argumentation. Another important future work is that standardization is in infancy, as many standards are still under development or have been very recently published. We still need time to synchronize everything to make it work smoothly. And scenario databases are another issue to be tackled. Okay, so therefore it becomes necessary to move to the next level of standardization in the concrete specification and demonstrate a commonly accepted safety assurance framework for the safety validation of SICAM systems. Okay, so future initiatives from the European Commission inside the Horizon 2021 program are moving in this direction and also will tackle these challenges. Okay, so thank you, Sitze. I give you the word.
Yeah, please stay available. Can the other speakers also open their camera? So thank you, Xavi, for your summary and wrap up. And we're coming to the close of the meeting. So you mentioned, Xavi, the international harmonization and showed all kinds of organizations that were involved. As I understand, there was a connection with Japan recently. There was a paper. Can you tell about that?
Can you repeat the question, Sitze?
There was a paper in a collaboration with Japan. Any of the other speakers can also answer this.
Maybe Jaco.
Maybe Jaco is.
Jaco, can you answer this?
Sorry, I missed the question.
The question is, recently in the collaboration with Japan, there was a paper published. Can you tell about that? What that paper was on HEADSTART and yeah.
I can answer that question.
Okay. In the room there is also Olaf Optekamp, colleague of mine, and he worked on that paper, so he can answer that question.
Yeah, thanks a lot. Actually, we have been working in the past half year on a white paper together with Japanese programs SEP-ADAS and Sakura. Of course, also in Japan, the concept of a type approval for automated vehicles is very important, and we have been looking between the two projects, HEADSTART and the programs in Japan. What were the commonalities and what were the differences, and where should we cooperate for the future? And actually, it was almost amazing to see how well the ideas in Europe fit with Japan and the other way around. And we identified also beyond the duration of the HEADSTART project to continue the collaboration with these Japanese programs, because it's very important. It's not a European issue that we are trying to solve. Actually, it's kind of a topic that we see all over the world, and that's where it's good that such a program in Europe fits well with ideas that are present elsewhere.
Okay, thank you. So clearly then HEADSTART is going beyond Europe. That's very nice to hear. For the attendees, there is one final question to the audience, and this is, you have seen all the results from HEADSTART, and the question to you is, when do you think you can start using this? When is this applicable for you? So we'd like your votes. Very good. I'll show it to you. So there is an even spread between less than a year, 1 to 2 years, and up to 3 years, which indicates that yes, it can be picked up quickly, but for some others it will really take some time to start using this. So good to hear this. Thank you. I've one last question to the coordinator and the speakers. So in the end, has HeadStart, Xavi or Carlos, has HeadStart made CCAM automated driving more safe?
Well, let's say that HeadStart itself does not make CCAM more safe. However, after adoption by industry, standards and regulations, it will help to make sure a new CCAM function is safe in the system, in the industry.
Yeah, okay. And if we look, the project will last 2 more weeks going into Christmas. So what happens afterward?
Well, at the moment, future initiatives from the European Commission inside the Horizon 2020 program are moving in the direction of standardization and also continue working to tackle the challenges that we have identified in HeadStart, and we will be working on in the next years. Okay.
So it's definitely continued by the EU in coming programs. Okay, there is a question about a bottle of whiskey by the audience. I skipped that one, I think, and it looks like preparation for Christmas. Thank you all for joining this meeting, especially the audience, and I hope this was very useful for you and will indeed be useful within a year, within 2 or 3 years, because we think that HeadStart has given, let's say, a comprehensive view on what you can do with scenario-based assessment. So I want to thank you all, and the slides will be made available on the HeadStart website, and once the deliverables are reviewed, they will all be available on the HeadStart website. So wish you all a very good time in the coming weeks, and have some good holidays, and thank you for attending. Bye-bye.
Bye.